Okay, let's see once how to apply exponentials now. Suppose you have two jars like petri dishes, something where bacteria or mold or algae could grow, and at noon, we'll call that time equal to 0, you've got 20 grams in here, and you've got 60 grams in this larger container. And you come back 5 hours later, and now this has grown to 22 grams. And the question is, what would you expect this to have grown to? And if you agree with me that you might expect it to go to 66, then what you're doing is you are assuming that the amount of growth, the amount of change is proportional to the amount there. Okay? You had 3 times as much there, and so you've got 3 times as much change. See that? And so if the amount of growth is proportional to the amount there, that's when you have exponential growth. Let me explain it to you. This is a review of what we did last time. Recall, here's e to the t. Here's t, and so here's e to the t. You go 1 unit away, t plus 1, and there's e to the t plus 1. So this difference right here, that difference right there is e to the t plus 1 minus e to the t. And if you compare that difference compared to the original amount, e to the t, okay, you look at that difference compared to the original amount, e to the t, let's do the algebra. You can factor an e to the t out. You're left with e minus 1. Now these two things cancel, and you just get e minus 1. That's just a fancy way of telling you that the amount of change, here's the amount of change, it's proportional to how much you have there. Notice that's totally different from a line. When you had a straight line, what was the amount of change? If this line had slope 2, if the slope was 2, then the amount of change was always 2. It didn't matter whether you were here, or whether you were up here, or whether you're way out here. The amount of change was always the same. See that? Amount of change as you go from one point to 1 point further, the amount of change is always going to be 2. But here, with exponential growth, the amount of change depends on how much you have to begin with. If you have more to begin with, you're going to have more change. And no matter what value of t you have, that amount of change is always the same. So that's key. That's a key idea and a key piece of understanding to see when exponentials are important when they're needed. Okay? So as soon as this is the case, then you know that it's going to be exponential growth, and so you know that the equation is going to be something of the form y of t is equal to e to some number times t, and there might be some initial amount, so you can put a there, and there's your general exponential formula. Okay? So let's now change this a little bit. Let's say that you have 2 different kinds of bacteria, and so now they have different rates of growth. And so let's say that at time equal to 0, they start out at 0 and 60. And now because of the fact that you have different rates of growth, let's say that at time equal to 5, this one has grown to 30, and this one, say, has grown to 70. Okay? So now the rates of growth, each one of them is still exponential, but the rates are different because which one is growing faster? Do you agree that this one is growing faster because this one added 50% and this only added about 15%? So at some point, this one is going to catch up with this one. Do you agree? And that's going to be the problem we're going to solve. We're going to find out when bacteria A catches up with bacteria B. So here's what we do. Let's let y sub A be bacteria, and let's not make that an A. Let's call that an alpha, just so we don't have so many A's in here. So bacteria A is going to be equal to alpha times e to the k t. And I need to find out both what alpha and what k are. And I can do that with this information. Okay, first of all, this is y sub a at time t is equal to that. Okay, so at time equal to 0, you stick a 0 in for t, you're going to get alpha e to the k times 0. K times 0 is 0, and e to the 0 is just 1. So that's equal to alpha. So alpha is equal to the amount at time 0, and we see that the amount at time 0 is equal to 20. Okay, the amount at time 0 is equal to 20, so that means that alpha has got to be 20. So right away, I'm starting to see what this equation looks like. It's going to look like this, e to the k t. Now what else do I know? I know that at time equal to 5, it's going to be equal to 30. So let's plug that in. If I put in 5 here, I'm going to get 20 times e to the k times, and now t is equal to 5, so it's going to be 5 times k, and that is going to be equal to, what's the amount of bacteria at time equal to 5? It's equal to 30. So now we can solve this for k. First of all, we'll divide through by 20. And if you divide through by 20, you're going to get 30 over 20, which is 3/2. Now we need to solve it for k. So this is where what I told you yesterday was important. We take the ln of both sides. Okay, 3/2 is bigger than 1, so that's going to be some positive number. Now the ln of e to anything just cancels. So I have 5k is equal to the ln of 3/2. And so k is equal to the ln of 3/2 divided by 5. So now I know exactly what this equation is. It's equal to 20 times e to the ln of 3/2 divided by 5 times t. That's for this one. Now let's find the next one. This is going to be y sub b now. Okay, there's some constant out front. Let's see if we can find these two constants. Okay, so first of all, at time equal to 0, you're going to get alpha times e to the 0. E to the 0 is 1, so that's just going to be alpha. And at time equal to 0, you have 60. So that tells me that alpha is equal to 60. So now I can write this. And now I'll do the same thing we did before. At time equal to 5, it's equal to 70. So at time equal to 5, I'm going to have 60 times e to the 5 times k. I'll write it as 5 times k, and that's equal to 70. I'll divide through by 60 and get e to the 5k is equal to 7/6. Take the ln of both sides. If I take the ln of this, I just get 5k. If I take the ln of this, I get the ln of 7/6. And so k is equal to the ln of 7/6 divided by 5. So there is the formula for how much bacteria is in this dish. So there they both are. Now we want to know at what time are they going to be the same? When is this one going to catch up with this one? So what do we have to do? We want to know at what time will this be equal to this. So I basically just set them equal to each other. And let's see once what happens. going to get 20 e to the, come ahead if you want, that's fine, e to the ln of 3/2 over 5t is equal to 60 e to the ln of 7/6 over 5t, and I need to solve that for t. What can we do? Well, let's see. Let's first, this t is up here. Let's first divide both sides by 20. That's easy enough. And that makes this into a 3. Okay. Now, what can we do next? I can divide both sides by this whole thing. So if I do that, I'm going to get e to the ln of 3/2 t over 5, all divided by e to the ln of 7/6 t over 5. That's all equal to 3. And now, remember what we know about exponentials? E to the a divided by e to the b is equal to the a minus b. Agreed? So here I can write this as e to the ln of 3/2 over 5t minus, let's see, what did we say? E to the a over e to the b is equal to e to the a minus b. So this is going to be e to this thing minus this thing. E to that whole thing is equal to 3. And now I can go e to the ln of 3/2 minus the ln of 7/6, all divided by 5, all times t is equal to 3. And now I can take the ln of both sides. If I take the ln of this side, ln of e to anything is just going to be this. And here's going to be the ln of 3. And then finally, here's my final answer. I'm going to get t is equal to the ln of 3 times 5, all divided by the ln of 3/2 minus the ln of 7/6. And I'm kind of curious what that is. Let's go ahead and see if we can figure it out. I'm going to go 3 ln 1.1 roughly times 5 is going to be roughly 5.5 on top. And on the bottom, I'm going to get this, and then I'm going to get this and subtract, and I get 0.25. So that's about the same as times 4. So 5.5, enter, 4 times, roughly in around 22 hours. Okay, roughly in about 22 hours, you'll have the same amount in one as the other. So nice problem, and that shows how you can use exponentials to solve problems like this. And the key is that we are assuming that it's exponential growth because the amount that's there is proportional to how much is present. Okay, let's do another one. There's lots of good ones here. Okay. Here's one thing Isaac Newton discovered. He discovered so many things. I'm doing all these from my kitchen, and in my kitchen, of course, I have my oven. If I were to take a hot pan out of my oven and look at the temperature of the hot pan, it turns out the temperature of the hot pan would be something like this. It's going to start very hot, it's going to start cooling very quickly, and then as it gets closer and closer to the temperature of the room, it's going to slow down, okay? It's never going to go lower than the temperature of the room. It's going to just keep getting closer and closer asymptotically to the temperature of the room. And the amount of decrease, the rate at which it decreases, depends on what this difference is. So there's another case where you have exponential decay in this case. We call it exponential decay because it's decreasing. And the rate of decrease is proportional to what this difference is. Here it's close to the temperature of the room, and so it's not changing very fast. Here it changed very fast. If I take a hot pan out, leave it for just a minute, I can probably touch it because it's cooled off very quickly within that first minute or so. So here's the formula. Put an alpha here again. And let's say that the temperature of the room is 70 degrees. Okay, let's just assume it's 70. In fact, let's just make this a problem of something that comes out of the oven. So at time equal to 0, at t equal to 0, here's the temperature of the room, and it comes out of the oven, and the oven is 350 degrees, and so at time equal to 0, it's 350. So from that, I can find out what alpha is. And so let's go ahead and find alpha. At time equal to 0, I'm going to get alpha times e to the 0. E to the 0 is just 1, plus 70. That's equal to 350. So that tells me that alpha's got to be what? Subtract 70 from 350, you get 280. So I know that y of t is equal to 280 e to the kt plus 70. Okay? And let's let t be in minutes in this case. And let's say that after 5 minutes, or let's say after just 2 minutes. Let's say that after 2 minutes, it's been sitting there on the counter and it's down to, say, 200 degrees. Okay? Let's say it's 200 degrees after 2 minutes. Okay? Now can we find our k? Let's see if we can find our k. So y of 2 is equal to 280 times e to the t is equal to 2, so it's going to be 2k plus 70, and we're saying that that's equal to 200. Okay, so if you subtract 70 from both sides, you get 280 is equal to what? 200 minus 70 is 130. Agreed? It's 130. And so now we can divide both sides by 280 and get e to the 2k is equal to 130 divided by 280, which is 13/28. Okay, and then you can take the log of both sides. If I take the ln of this side, I just get 2k. If I take the ln of this side, I get 13/28. Okay, and so finally k is equal to the ln of 13/28 all divided by 2. So here's my formula. Y of t is equal to, what did I say it was? 280. E, here's my constant, ln of 13/28 all divided by 2 times t plus plus 70. There. So there it is for any value of t. So say we want to know what the temperature is going to be at, say, 10 minutes. So we go y of t is equal to 280 times e. Well, let's see. If t is equal to 10, 10 over 2 is 5. So it's going to be 5 times this quantity plus 70. If you calculate that, this whole thing here gets to be about 0.02, and so you multiply that by 280, and you get about 6, roughly 6.04 plus 70 is about 76.04, so about 76 degrees. So you see that it's gone down to pretty close to the room temperature by the time you get to even 10 minutes, assuming this is right, which actually it's probably going to cool off even faster than that. Okay, finally, let's do one more. This one is radioactive dating, carbon-14 dating in particular. Here's the idea. Suppose you have 2 lumps of carbon-14, something like this, and here you have a bigger lump, and say this is 2 pounds, and say this is 10 pounds. Okay? And it's all carbon-14, and you leave it for, say, 50 years. I'm not sure exactly what the numbers are, or 100 years or something like that. Maybe you leave it for 100 years, and you come back, and some of this carbon-14 is turned into, I'm not sure what it turns into. It no longer is carbon-14. So say you lose 2 ounces of it. Let's say that just for sake of argument, you lose 2 ounces of it. You agree that over here, you would expect to lose 10 ounces of it. And as soon as, again, you say that, you're saying that the amount of increase or decrease in this case, is proportional to how much is there. And that would be very reasonable because carbon-14, it's just doing its own thing. It's just, billions and billions. That's way too small of a number of atoms. And those atoms don't care what the temperature is or what's going on outside or what's playing on TV or whether you're throwing it up in the air or the pressure, anything. All those atoms are just doing their own thing. And so if 2 pounds gives off 2 ounces, then 10 pounds is going to give 10 ounces. So that's how, as soon as they know that, then they can use carbon-14. Then right away, you know that carbon-14 has exponential decay. And in order to figure out what that exponential decay value is, all you have to do is take the amount that's there several different times, and then you can find the constant, just like we did with our temperature. You can find the constant, and then from that you can start calculating how old things are, because if you know how much originally was there, can guess at that, then you can figure out how much has changed, and so you can get the age of things. So this is very good for figuring out the age of bones and things like that we find that are in the thousands of years old. You can also use radium radioactive dating to figure out the age of the Earth in the same way. And the age of the Earth, you can calculate very, very accurately to about 4.5 billion years old. So that's all very important stuff that can be done with radioactive dating. All depends on the mathematics of exponential decay. So anyway, after doing all that, here's what scientists have determined. The rate of decay of carbon-14 is given by E. Notice this is a negative number, which means it's going down. Given by that. And so that's a very small negative number, so it's decreasing very slowly. And quite often when you have something that's decreasing, what you often ask about is what's its half-life? How long does it take to lose half of what's there? So notice y of 0 is equal to what? you don't have anything here, so you can assume it's a 1. It's 1 times e to the 0, which is 1. So the original amount we have here is 1. So you often are interested, kind of a nice way of determining, saying how fast something decays is by saying how long does it take to lose half of what's there. So let's find the half-life. Find the half-life. Okay, and that's easy to do. All we do is we say, for what value of t, which is going to be e to the 0.0001216t, is that going to be equal to half of the original amount? So is that going to be equal to 1/2? Okay, so all we have to do is solve it for t. So if I take the ln of both sides, the ln of e to anything is just that thing. And that's going to be the ln of 1/2. And now I solve it for t. So t is equal to the ln of 1/2 divided by, and this is a negative right there, so I should have had a negative right there. And so this should have been a negative right there. And so now I'm going to divide through by negative 0.0001216 t. Okay, let me make sure I did it right. That's negative. So that's all negative. So e to the ln of it, ln of e to anything is just that thing. So here I have this thing is equal to the ln of 2, or ln of 1/2 rather. And so t is equal to the ln of this divided by this. And so that's easy enough to do. I'll do it right here. I'm going to go ln, enter, 0.0001216 divide, and I get very close to 5,700, just a tad over, 0.22. Okay, and that's in years. Okay, that's years. So in other words, it takes about 5,700 years if you had a big lump of carbon-14 for half of it to disappear. And then half of it disappears, and once half of it disappears, you know that that much time has gone on. If 3/4 of it have disappeared, then you know that this times 2 has happened, and so on. And so that's where that can be very helpful. Okay, very good. So that's a lot of stuff on exponential functions and their use. They're used all over the place because there's all sorts of things in the natural world. What are some other things, by the way, besides what I just mentioned? I mentioned population problems, and we mentioned carbon-14 dating, and we mentioned Newton's law of cooling. Another one is drugs in the body, the rate at which drugs decline in the in the body, the kidneys pull it out. Interest rates is another one. Interest rates in banks. That's hopefully going to be exponential increase, right? That's going to be exponential increase, interest rates. Okay, very good. So in fact, that just reminds me I'm going to do one more problem. I'll save that for the next video and do one more on this just to show you something kind of cool about interest rates. So hold on. Very good.